Welcome back. This is the first lecture in a series of brief lectures on the fundamentals of fuel cells. So this lecture will be predominantly from this reference, and some parts are from this particular reference. Why are we looking at fuel cell? We have already looked at the fundamental distinction on the advantages of electrochemical energy conversion. We have looked at this feature on how the Carnot limitation is not a constraint when it comes to electrochemical energy conversion. So please look at this lecture. Even contrasting with batteries, fuel cells have some advantages. So which is the ideal electrochemical energy conversion uh, device for, let's say, transportation systems, whether batteries or fuel cell? It has a lot of intricate issues when we try to debate between these two options. But in any case, what we are going to be looking at are fundamentals of fuel cells, which is sort of important in understanding electrochemical energy conversion and storage devices more broadly. In addition, there is another aspect which is very important. Fuel cell is just the exact opposite of an electrolyzer. For example, the simplest of fuel cell is the hydrogen oxygen fuel cell. Hydrogen is continuously supplied, and oxygen is supplied via supplying air. Okay, so when you supply hydrogen and oxygen, the product of the fuel cell is water and electrical power. So this is exact opposite of an electrolyzer. In an electrolyzer, you supply water and you supply external power, and you generate hydrogen and oxygen. So much of the design principles which are going to be used in fuel cell, let's say especially when it comes to stack design and so on, design of porous electrodes and so on, so are also relevant for water electrolysis specifically, and in general other electrochemical reactors, for example in electrochemical CO2 reduction and so on. So these principles are fairly general. So let us get started on understanding fuel cell via a simple schematic. This has nothing to do with the real engineering design. This is just a schematic wherein hydrogen is supplied on one side onto this porous catalyst. Because oxygen separation from air is fairly expensive, you typically do not send in pure oxygen. Instead, you just send in air, and oxygen is part of air, so that gets reacted. This also tells you other issues that are relevant for the commercial prospects of fuel cell. The overall cost must be less. Therefore, in all approaches to decreasing cost has been attempted when it comes to commercializing fuel cell. For example, instead of sending in pure oxygen, you supply air. But when you do that, air might have other impurities like CO2. This CO2 might react with the alkaline electrolyte. So this is electrolyte does not flow into the cell. It is just what this arrow indicates is that this part is just the electrolyte. Okay, this indicates the flow direction. Hydrogen comes in this manner, gets partially reacted, and leftover hydrogen gets out this way. Air comes in this way, partially reacted air gets out this way. So CO2 might react with um, the alkaline electrolyte. Okay, so this is not ideal. And reaction of Faradic reaction of oxygen is a challenging task. Okay, so oxygen reduction is a big issue. Hydrogen Faradic reaction is not such a big issue, but oxygen reduction is a big issue. So cost is an important aspect when it comes to commercial prospects. And therefore, even though fuel cell was demonstrated way back in late 1800s, okay, it's been there for quite a long time. Large scale implementation of fuel cells has not yet been done. So at the cathode, we have oxygen getting reduced to hydroxyls. So this is a particular form of fuel cell, let's say alkaline fuel cell. And the hydroxyl so generated gets transported across the electrolyte, goes to the anode, and water gets formed. Okay. So this in principle, this great, right? You just supply air and hydrogen and you get CO2 free um, products and you get electrical power. But despite this apparent simplicity, the commercial prospect has been daunting. While this set of lectures do not focus too much on material challenges, we have addressed some parts of it in another playlist called Design of Electrochemical Materials. But we'll also touch upon some aspects of material challenges as we progress in this series. So, hydrogen being a gas, it has certain advantages and disadvantages. The energy density per unit mass is very high for hydrogen, so it's a great fuel and it produces just water, right? So in that way, oxidized hydrogen is great, but because it's a gas, the volumetric energy density is very less. So handling hydrogen is challenging. So you want to move away from hydrogen to some other fuel that can be more easily handled. So typically, liquid fuel um, is much better in terms of the way it can be handled. Its volumetric energy density is higher than hydrogen, but energy density per unit mass is lower than hydrogen when it comes to methanol as a fuel. A battery uses in a way a solid fuel, right? All the fuels that goes into a battery is like a batch reactor, whereas a fuel cell is a flow reactor. So the fuel in a battery is a solid fuel, but the fuel in a fuel cell is a liquid fuel. In this case, let's say methanol fuel cell. So we will clarify what we mean by direct methanol fuel cell in the next slide. So here, the anode reaction is methanol reacting in this manner, generating these products. So as soon as you see this reaction, the complexities should become obvious. First, it involves multiple electron transfers and multiple bond breakages are involved. Therefore, the electrocatalytic challenges is fairly um, daunting. Okay, so the O potential associated with this electrocatalysis can be significant, so which goes towards decreasing the maximum voltage which you can get from these fuel cells. So on the cathode side, it's not very different. Oxygen, this again still a hard reaction, generates water. So both on the anode side and the cathode side, you have rather difficult reaction that has to be electrocatalyzed. So a lot of research has gone into developing electrocatalysts for direct methanol fuel cell. So the overall reaction is shown here. So when you go from an exothermic reaction to understanding the potential, we use this simple relationship, which we have discussed earlier when we looked at electrochemical thermodynamics. The delta G of this reaction um, is here. This involves 2 moles Therefore, in 2 moles involve 12 electrons, whereas 1 mole involves 6 electrons. That goes in here. And the maximum potential that you can get just based on thermodynamics is this value. Even though you may get this value from thermodynamics, there are a lot of other O potentials associated in electrocatalyzing this reaction and electrocatalyzing this reaction that would decrease the voltage which you can get from just from pure thermodynamic arguments. So let's try to understand what we mean by direct. So typically, because this reaction is hard, that is, instead of sending in methanol directly into the fuel cell, you may want to process the fuel in some other manner. Okay, so here the fuel is methanol. You may also have natural gas, methane, as a fuel. And how do you want to process that? Ideally, you want to reform this fuel to form hydrogen. Okay, so you want to be just sending in hydrogen. This reaction is called a reforming reaction. This is ideally done in an heterogeneous catalysis manner. So this well-studied reaction in heterogeneous catalysis. So you have nickel catalyst operating at high temperature to do this reforming reaction. Whenever we talk about reforming, we are generally talking about how to obtain more of hydrogen. So this is a fuel, but this is a better fuel. So hydrogen can be further supplied to a fuel cell. So instead of directly supplying a fuel, in the previous case, you directly supplied methanol. You can also have fuel cell where you directly supply methane. So instead of doing that, you may reform the reaction, get hydrogen, and then supply hydrogen to the fuel cell. So the important things to understand is when the kinetics is slow, in both these cases, kinetics is slow, activation over potential becomes substantial. So in general, the voltage that can be obtained from a fuel cell will decrease. So in these cases, electrocatalysis is an important component of a fuel cell, and these electrocatalysts can be fairly expensive. Okay, so this increases the cost of a fuel cell. That's an important challenge. So one of the widely studied electrocatalysis are to do with oxygen reduction in a fuel cell. Okay, there are a lot of good theoretical models, and enormous number of experiments has been done to develop new catalysts. And even with such an enormous amount of effort, significant decrease has not been obtained in the O potential. That is to do with something called scaling reactions. These are not the main discussion points of these lecture series, but if you're interested in these things, please look at other playlists wherein we look at quantum chemical models on how to design electrocatalysts for a fuel cell. So other important challenge are membranes. Okay, so these membranes sometimes are a monopoly of certain companies. For example, in the proton exchange fuel cell, the best membrane, Nafion membrane, is again expensive. Both the membrane and the electrocatalysts are great impediments for commercializing fuel cells. Let's move on. So the efficiency of a fuel cell is given by these expression. This is specifically to do with voltage measures of efficiency. So rate of electrical energy obtained from a fuel cell divided by the maximum rate of electrical energy. That's a measure of efficiency. Electrical power from a fuel cell divided by theoretical power. So let's understand how you go about computing this. This is the mass flow rate of the fuel that is getting into the fuel cell that is supplied in a continuous manner. Dividing by the molecular weight, you would get the amount of moles per unit time times the delta G of the reaction, right? So this quantity goes into this quantity. From here, we can get the what is in the denominator. Okay, so this is completely based on thermodynamics, right? So on the numerator, we have VI, which is just the power, right? So um, um, from this, you may get V divided by U. This is a measure of efficiency of a fuel cell. How to think about efficiency can be quite complex. We will be discussing, we'll be revisiting and discussing this topic in some later lectures. So, but as a preliminary introduction to efficiency, we are providing this formula. So, as stated earlier, fuel cell is an open system. It's not like a batch reactor, like a battery. Here, the fuel and the oxidant that goes towards oxidizing the fuel um, is supplied in a continuous manner. This is an open system. If you have an hydrocarbon fuel, you will get carbon dioxide and water. If you have hydrogen as the fuel, you will just have water as the product. You will get electrical work. There might also be certain heat exchanges, right? So when you have delta G of a reaction, delta G is delta H minus T delta S. This T delta S component goes as an important implication to heat exchanges between the fuel cell and the environment. We may look at these issues from basic thermodynamics in some later uh, lectures, but in this slide, we are just emphasizing that fuel cells are open system and the thermodynamics itself can get complicated in some manner. In the next lecture, uh, we will talk about the different types of fuel cell, just to give you an idea or what are the options that have been looked at when we have tried commercializing a fuel cell. Thank you.